Hello everybody. So in this next video, what we want to do is take these calculated theoretical compositions and compare them to the natural compositions. So we want to see if this idea of perfect fractional crystallization can actually describe what we see in nature. Now, I am going to make a copy of the MGO column here. And I'm going to do this because when I create a chart, Excel will always take the left-hand column and use that as the x-axis. So I'm going to take the magnesium and silica columns. I'm going to hold down the command key to select the second column. I'm going to copy those and go over to magnesium versus silica and hit Edit Paste Special. And there's our curve. Now, to make this curve a little more obvious, I'm going to give it a solid line. I don't want the markers to look like data. I'm going to make them as hash marks, and I'll make them very large so they're easier to see. And then we'll check to see if they do a good job of explaining the data. Well, they do kind of. They don't follow the trend, that's for sure. But they do allow us to get to from the primitive compositions right through the evolved compositions. And that's just dumb luck. I didn't know that that would happen on our first try. So we are explaining these. We're explaining these highly evolved compositions. We can make these rhyolites by pure fractional crystallization. The one problem we have is we can't make these guys here. We're not explaining these intermediate dacite or andesite compositions. Let's try plotting MgO versus calcium and see what happens there. So we'll copy those. We don't need this line from the previous lecture. Go to Edit Paste Special, New Series, Categories and X values. And again, we have a curve. And this curve does a very good job of explaining the evolved compositions. I'm going to make the markers hash marks. Well, not quite. We don't quite get as low a calcium content as we see here. So the model explains these rhyolites in terms of their magnesium and silica contents, but the model still predicts that we should end up with 1.3 weight percent calcium when we really only have 0.48. And we're not explaining any of these compositions here. So we'll go back to the modeling sheet. Well, what can we do? Well, if the calcium content is not low enough, we can increase the amount of plagioclase. So instead of 0.3% plagioclase, let's make it 0.5. And this goes up to 1.2. Let's make CPX go to 0. Well, that didn't decrease it the way I thought it would. Clinopyroxene is absorbing some of the calcium, so let's decrease the olivine content. And that should increase the D. I think it did. Yeah, now we get a very good explanation. Now with by decreasing the amount of olivine and increasing the amount of plagioclase and CPX, we've increased the D. So originally we had values of 50% olivine and 30% plag, 20% CPX, and the D for calcium was just 1.685. And we had a poor fit to the calcium. But if we go back and decrease the olivine and increase the plag and CPX, the D goes up a little bit, and it goes up just enough to explain those. Now, that will also affect our values for silica, and we've changed our silica curve, but we're still getting close to our values here for the rhyolitic compositions. So I'm not going to go any further than that. What I want you all to do is play around with the mineral compositions and make charts for silica titanium, aluminum, iron, manganese, calcium, sodium, and potassium. Add these theoretical curves to each of your charts and do the best you can to make them fit as well as they can. Some might fit very well and some might not fit very well at all. But that's okay. Remember, all models are wrong, some are useful. We're just trying to see if we can explain as much variation as we can. And then in the last lecture, we'll look at a different way of explaining the data, and we'll see if we need a different kind of process to explain the full range of compositions that we see.